presentarlo al doctor Cameron Abrams. Él es profesor titular y director del Departamento de Ingeniería Química y Biológica de la Universidad de Drexel en Filadelfia. Obtuvo su título de grado en Ingeniería Química en la Universidad Estatal de California del Norte en 1995. Se doctoró en Ingeniería Química en la Universidad de California, Berkeley en 2000. Y realizó un postdoctorado en el Instituto Max Planck en investigación de polímeros en Mainz, Alemania. Desde entonces, Abraham ha dirigido numerosos proyectos de investigación, incluyendo 17 tesinas de grado, 19 becarios doctorales, 2 maestrías, 11 postdoctorados. Es un científico destacado en el área de las simulaciones computacionales sus trabajos cuentan con más de 4.000 citas y alrededor de 300 citas por año se van implementando. Ha realizado importantes estudios de la cinética y termodinámica de proteínas, en el diseño de inhibidores de entrada del virus del HIV, funcionamiento de receptores de insulina, factores de crecimiento y muchos otros sistemas. El doctor Abraham es especialista en el desarrollo de métodos acelerados de simulación y demostró eficiencia de superficie de energía libre. Entre otras distinciones, Abraham ha recibido el premio Carrier de la National Science Foundation, el premio al impacto de ciencia e ingeniería molecular computacional, otorgado por el American Institute of Chemical Engineers, y fue elegido miembro del American Institute of Medical and Biological Engineering. Cameron fue mi supervisor en mi postdoctorado, pero más que un simple jefe, él fue un mentor. Aprendí muchísimas cosas de él y en los 2 años que yo estuve fue como hacer otro doctorado. ¿Está bien? Aprendimos un montón juntos. Él es una excelente persona y la forma que investiga, humilde y entusiasta, es para mí una admiración. Sí, le vamos a hacer la entrega del diploma de visitante distinguido.
Ok. Bien, bueno. Congratulations.
Thank you.
The resolution is in Spanish. It is the official document that you are the English professor of our faculty.
Wonderful. Thank you
But
so much.
it's in Spanish.
Okay.
Okay, thank you very much.
Thank you. Yes. Oh. Well, good morning, everyone. It's very nice to be here, and I want to thank the Dean and the Vice Dean for their wonderful welcome and this great honor. I very much appreciate it. I don't know everything Alexis said. I will say one thing about Alexis. I learned more from him than he learned from me when he was my postdoc. So I'm very happy that we can continue to collaborate. So thank you, Alexis. As Alexis said, my name is Cameron Abrams. I am the Bartlett Berry Professor and Head in the Department of Chemical and Biological Engineering at Drexel University. Drexel is in Philadelphia. Philadelphia is a city like Cordoba, about 2 million people, several universities, small universities compared to the universities here, but a nice place to live, and the weather is different. We have snow in the winter. We had a nice snowy winter this year. So anyway, I'm very happy to be here to present some of this work, and I hope this, maybe I'm too far from the, let's see, if I get closer. The professional.
This to go forward.
I see, I was going backwards.
Yeah.
And there wasn't backwards.
That's why.
There's no slide -1. Okay, thank you. So I'll introduce the basic motivation for most of the work I talk about today. And then I have 4 different methods I'd like to give you just a preview or some examples about. They're all based on temperature accelerated MD, temperature accelerated molecular dynamics, on the fly parameterization, which is a derivative of TAM, temperature accelerated MD, the string method, and Markovian milestoning. And then finally, if I have time, I can summarize. Okay, to introduce. So this is a plot of time versus length of the universe. So several important time and length scales of interest. I don't necessarily ask you to read and understand all of them, but I want to focus on the region of physical phenomena that molecular dynamics simulation is comfortable working in. So time scales that are between a picosecond and a microsecond, length scales that are between a femtometer and perhaps a micron or a little bit less, okay? So the kind of phenomena that happen here, we're quite used to studying with MD, but the interesting, sort of biologically interesting phenomena occur on much longer timescales. So the problem with MD to try and get to these much more interesting biological phenomena is to increase the timescales that they can access. So what is molecular dynamics? And again, the problem with MD is down here. The problem is that we move time forward in molecular dynamics simulation. One increment of time is a femtosecond. And you need hundreds of millions and billions of femtoseconds to come to macroscopic timescales. But in MD, of course, we set initial positions and velocities. Forces are calculated from potential energy function, which tells us the interatomic interactions among the atoms. We then use straightforward numerical integration to get new positions and new velocities of all of the atoms. We may want to sample. If we do, we save a sample. If we don't sample, we then ask, are we done? That is, have we run for enough time steps? And if the answer is no, we just repeat the process. Okay? And in that way, we can accumulate picoseconds, nanoseconds, and if we're lucky, microseconds of actual time following the atoms. So in order to understand what we get that's useful from MD simulation, we have to understand microstates and macrostates. So on the left is a macrostate. It's water in a jar. And it's at a given temperature and a given pressure. So its equation of state tells us exactly what thermodynamic state it's in. On the right-hand side is, and how can I make the movie play? I guess that's another question for the I know I can make the mouse go to the little play button, right? Okay. So microstates, this is also water, a model of water, where we're just taking a snapshot every picosecond or so and watching the atoms move around. But that's a series of microstates. And of course, everyone knows in statistical mechanics, you average over these to tell you something about that, right? So that's what we're trying to do. Okay. So of course, the notation here for microstate, I'm saying a microstate is basically the set of positions and velocities. In stat mech, every microstate has a probability of being observed, P sub nu, and then any observable quantity that can be computed for a microstate can be averaged over microstates to get you the observable value. That's the G inside the brackets here. So of course, one needs to know all of the states and each state's probability in order to get an observable value. What MD does is forces us to make an assumption or forces us to adopt the ergodic hypothesis. The ergodic hypothesis says, well, we don't need to know P sub nu. We simply infer it by doing uniform random sampling from an MD simulation. So as the simulation is running, we sample every so often, and we assume that the simulation is an equilibrium simulation. It is every sample we generate is statistically valid. It has its right statistical weight. The ergodicity, the property of ergodicity, requires that we sample infinitely. We have to have an infinite number of samples to guarantee that this is the true observed value we would get if we knew all of the probabilities. So this is the assumption we're making, and it's never correct, right? We almost never achieve ergodicity in a real MD simulation. So almost everything I do is try and get around that problem. So feature space is what I want to talk about next. So in feature space, we're thinking of a smaller variable space where we create the variables that we're interested in. We choose what we're interested in learning about. So just generically speaking, I may have a two-dimensional feature space, and I'm interested in locating some particular place in that space that's a minimum, right? Or most probable observed space. So in order to understand feature space from an MD simulation, we have to compute an ensemble average of a particular quantity. In this case, it's the mapping function. So we want to map our MD system, the configuration of the MD system, to a point in our feature space. So this is just a histogram when we do an MD simulation. We just histogram, we sample our space, and every time we sample our configuration, we decide which bin in feature space that sample belongs to, and we accumulate bins and we get statistics. So that gives, and this, when we do the Boltzmann inversion, right, minus KT log of the histogram, we get what we call the free energy. It's just a statistical representation of the actual equilibrium system in feature space. Okay. So we think of running an MD simulation where we take all of these little samples here. So these are literal snapshots. You may not believe me. Literal snapshots of a liquid argon simulation. Very few atoms. Okay, so yeah, I wrote Python code to make this figure, right? But each one of those is a snapshot, and each one has a unique mapping into this two-dimensional plane, right? And they follow a trajectory. This is not real. At this point, no longer real. they follow some trajectory in this space. And I'm trying to indicate that, yeah, the space has a local minimum that the system is orbiting. Okay. So once we have this idea of feature space, now the question for MD simulation or accelerating MD simulation is, how do I use the least amount of computational power to generate as many samples as possible to give me the best representation of feature space? Oops, okay. So this brings me to the extended Lagrangian formalism. In the EL formalism, we extend configuration space. So not only do we have the variables for the configuration of atoms, we add degrees of freedom that correspond to locations in feature space. So that's what I mean here, where I have the X's are the positions of all the atoms inside each little sample here. The orange dots are the Z, the degrees of freedom for locating in feature space. And by extended Lagrangian, what we're saying is that now we've added a new term to the forces, or a new term to the potential energy, that tethers the atom projections to the locations in feature space. So these are tethered together with a spring. And I don't know if you can see the detail here, but the actual projections are in black, and the Z degrees of freedom are in orange, and they're not perfectly overlapping, right? They have a little bit of space between them because of this finite spring constant. So the Z variables can either follow along with the projections of the X's in feature space, and how closely they follow is determined by how large that spring constant value is. But these are degrees of freedom, so they also obey equations of motion. The Z variables are also moving according to some mechanics, and it has, of course, because the overall system is Hamiltonian, this term has to be what are the forces that govern the Z variables. Okay, so there's now the Z's can move, and we can determine how easily they move by putting a bias into their equation of motion. So that bias might be a very high temperature, for instance, make the Z variables very hot. So they move around in their own space very quickly, but they're still tethered to the atomic projections. Okay, so that brings me to temperature accelerated MD. This is the theory. It was developed by Luca Margagliano and Eric van den Eyden back in 2006. That is to start with an extended potential energy that has this mapping function, this tether to the atomic degrees of freedom. The configuration of variables have this equation of motion in the middle that has, we can, of course, thermostat them so that we can run in a constant temperature ensemble or a constant pressure ensemble. And then the auxiliary variables in TAM, instead of working with a formalism where we have acceleration, we work in a Brownian formalism where we simply work with velocities instead of acceleration. So in this case, we don't have inertia for our Z variables. The important point, however, is going from this expression to this expression. This quantity here, which is basically the force that keeps the Z variables and the projected atomic variables in feature space close together, if you thermodynamically average or ensemble average that quantity over time with the Z variables constant, okay, and take the limit as the kappa value gets very large, that becomes a mean force. Because when this is average, this is a mean force in the space of the Z variables. So what that means is that if we run this system, we decouple these equations in such a way that these dynamics are much slower than those dynamics, then this force on the Z atoms becomes the gradient of a free energy, the negative gradient of a free energy. So we're actually letting the Z variables experience the thermodynamic equilibrium free energy and move on that surface as if it were a potential energy, as if it were temperature independent, okay? So it's something that's calculated by the atomic variables, because that information is in the atomic degrees of freedom, but the Z variables can move on it independently, okay? And that's by essentially taking the Z variables to be very hot compared to the atomic variables, okay? And that gives us this enhanced sampling in feature space. Okay. So this is an example of trying to do conformational sampling using TAM. This is from the paper that Eric and I published several years ago, where we introduced TAM for protein conformational sampling. What you're looking at is, this is a piece of the spike protein for HIV. Okay, so HIV spike protein is a trimer of dimers. And this is one monomer from the dimer, and it's not a complete monomer. It's a piece of a monomer, but it's the most famous three-dimensional structure of the HIV surface protein published up to about 1998 or so. And you're seeing two structures here. One that's colored with the sort of blue and red, that is the default ground state for that protein. When a particular antibody binds to that protein, it adopts a different conformation where these two loops here flop outward, and this helix, you can't really see in the background, it adopts a slightly different twist. So that becomes a stable state as well. This state, this conformation has never been published without the antibody bound to it, but it must be a conformation that's adopted. And so we challenged TAMD to try and find this conformation starting from the default ground state. And of course, if we start in the default ground state and run a long explicit Solomon MD simulation, you can run for hundreds of nanoseconds, it stays there. It's a very stable state. So instead we used TAMD, in which we picked, in this case, 23 unique centers of mass in the protein, okay? And accelerated their Cartesian variables using TAMD to about, I think it was 3000 Kelvin for that degree of acceleration. And we ran a bunch of TAMD simulations. And what we're tracking here is the root mean squared deviation between the simulation and the reference structure, the default intermediate state, or the default ground state. We're the RMSD against the target state, against the target state. So a low value in this axis corresponds to a closer match with the target. Now the important thing is that the dynamics don't know about the target. This is not targeted MD. We're not putting the target into the dynamics. We're letting the dynamics explore conformation space, and randomly, again, it doesn't happen all the time, but randomly one trajectory will get very close to the target state. And this particular red trajectory got very close. It got within about 4 angstroms RMS to the target. It's clearly not a perfect match, but this proved that we were able to do this enhanced conformational sampling with TAMD. Okay, so that brings me to on-the-fly parameterization. What TAMD does not do by itself is tell you the free energy. It uses the free energy as a potential energy, but it doesn't tell you what the free energy is. You can't make a picture of the free energy. But there are lots of MD-derived methods for showing you free energy. Metadynamics, metadynamics is the one that comes to mind. This is the one I like the least. But there are many. Sorry, ABF, another one I don't like very much. Yes. Okay. That's adaptive biasing forces. We decided to try and come up, Eric and I decided to try and come up with a new method to get the energy from TAMD. Since TAMD is doing this ensemble average of the mean forces anyway, we're not actually asking what those values are. Let's ask what they are. And if we then say, okay, take a target, basis function expansion of the free energy, okay? We use essentially an optimization scheme where there's a matrix that's parameterized where we are going to tally up this ensemble average, okay? So what does this mean? These are the mean forces coming from the TAMD simulation. So every single time step, I get values for this for every degree of freedom. Every Z variable has a value for this. I have a basis function expansion. I've assumed some values for the lambdas. The phis, of course, are basis functions. So I have a value for this, the approximate gradient of the free energy, or say the basis function expanded form of the free energy. And the difference between these two things is an error. Of course, if I have to square that, of course, that gives me an error. So I ensemble average that error, okay? I want to find the values of lambda that minimize this. So that's a matrix operation you see at the top, right? Set the derivative equal to 0. You turn into a matrix equation, invert the matrix, and you get lambdas. Those lambdas are the parameters in the free energy. So essentially what we have, or exactly what we have, are these two quantities that have to be tallied during an MD simulation. To tally this matrix here, so that those set of matrix elements, which are of course coming from the basis functions, and because we can choose very simple chapeau basis functions, these terms are very easy to evaluate, very, very fast. And then we have the forcing vector here that has the mean forces. Okay, so if we accumulate these matrices for ever how long we want to run. It doesn't matter how long, we can run for as long as we like until the values stop changing, basically, and then we can invert that matrix and get the lambdas. On the lower right here is a very, very simple proof of concept that one can get the free energy profile for, that's butane. Okay, so we have the trans state of butane here. We have the two cis states or the two gauche states here, and there's of course a barrier between them, very small. So you can run an MD simulation of a butane molecule. It's a very good project for a high school student if you like, and then just tally up the value of this, and these are in radians. So this is a distance in angstroms. I'm sorry. So it's the distance between these two, the C1 and C4 atom of the butane. So these are distances. And tally up the distances that are observed, Boltzmann invert, get the histogram, get the free energy. Okay, takes about 300 nanoseconds to sample from that point to that point and get the black curve. 1 nanosecond of OTFP gets you precisely the same data. And it also gets you data in a regime where MD simply can't simulate at all, right? Because we're running at 300 Kelvin, we're never going to get free energies that are above 6 kcals per mole above the minimum. But with MD, it's trivial, easy to get that stuff. Okay, so that's a toy example. Let's look at a real example. And this is some of Alexis's work with me back in the day when we were studying ion channels. So this is a potassium voltage-gated, an example of a potassium voltage-gated ion channel. Okay, there's a picture from the PDB on the upper left. We're focusing in, if you were to imagine being able to look through right in the middle, the dead center of this sort of symmetrical protein, there's a channel through which potassium ions can go from inside the cell to outside the cell. And there are several well-characterized locations where the ions are thought to sit, based on the fact that there are side chains coming, or backbone carbonyls coming from the protein atoms that form these collars, or these places where the potassium ions can sit. Okay, so the question becomes, how does one translocation event happen to get a net transfer of one potassium ion from inside the cell to outside the cell? Okay, so the selectivity is not really well understood for these ion channels. This is a plot where we're tracing several quantities. Their Z position, so Z is this direction, the Z position of several quantities over time in a fairly short MD simulation. The red curves are individual potassium ions. Okay, so they start off in these 3 canonical positions, and then as the simulation runs, we see an event where they all 3 shift up by 1 position, and they shift back down, and they shift and do a little bit of shifting. We have the yellow, which is the average of the top 2 reds. Okay, and so we wanted what Alexis actually thought. Well, let's run on the fly, or TAMmed, and then on the fly, where our degrees of freedom are the Z position of this ion and the average Z position of those 2. And why do we do that? Well, it's a 2-dimensional system at that point. We want to have a 2-dimensional representation of the free energy. It's easy to see, easy to understand, than if we were to have a 3-dimensional version. So that's what we started with. Okay. So after many TAM simulations and OTFP reconstructions, these maps of free energy illustrate for us a thermodynamically likely mechanism for the transport of 1 potassium ion. So I'm showing the degree of freedom, that's the Z position of the inner ion on the y-axis, the center of mass of the 2 outer ions on the x-axis. So let's look at this map here first. So this is a 2-dimensional free energy surface computed using on-the-fly parameterization and TAMD simulation. So we start off in position A, okay, where we have the center of mass of the outer ions at this particular position, the center of mass of the inner ion there. The first thing that happens is that the inner ion moves, right, while the outer ions are not moving. Okay, and we reach this minimum here. At that point, the outer ions move without the inner ion moving. So we call that a knock-on mechanism. The inner ion goes up first, and the 2 outer ions shift upward by 1. So there is a direction. There's an order in which that happens according to this map. So an alternative could have been, well, what if the outer ions move up first, and then the inner ion jumps into the space that they leave behind? That is not thermodynamically predicted. Okay, so there's an important distinction from this prediction, is that the inner ion moves up first, and the outer ions then move up by 1, right? And then once they moved up by 1, the inner ion can move up by 1. We've had a net 1 translocation at that point. So this is the case where the inner ion has moved. Inner ion moves, outer ions move, inner ion moves, and we've had 1 translocation event. Okay, and of course, Alexis being the careful scientist that he was, I assume he still is, took error measurements, all right, did statistical average errors of the free energy surfaces to prove that we're under a kcal per mole in error, which is the standard for most of these free energy calculations. Okay, so the next question Alexis asked is, what role is water playing? Water, of course, potassium ions don't exist in, near ion channels without being solvated by water. So what role is the water playing? And so we asked the question, well, what happens if we force water to go along with every potassium? We actually tether a water molecule to every potassium ion so that nothing dries out. And this is the translocation signature that we get. It's very similar to the knock-on mechanism. It's slightly more smoothed out, but it's very similar. Okay. If we instead forbid water, just say no water is allowed in the channel at all, and then what happens? We see this very detailed knock-on mechanism that goes ladder by rung by rung in the ladder, very, very detailed stepwise mechanism. So it seems the role of water is pretty clear. It's what you would think. It lubricates the translocation of potassium through the channel. This is a much more stepwise approach. However, if one were to calculate the free energy cost to go from state A to state D to get one translocation event, the overall cost for that translocation is less than this. Okay, or I would say the cost, the barrier height. So the cost to get over the first barrier is higher to go this way than it is to go that way. Okay, so it's a little unclear. With water excluded from the channel, there's a lot less concerted motion. It's a lot more knock-on like, but it's a lower free energy barrier. Okay, great. So now let me move on to string method. Okay, so I've talked about simulating, say, one MD system, like one MD simulation that maps to one point in feature space. Okay, with string and feature space it's important because there's multiple places in feature space we would like to understand. In fact, we would like to be able to go from some minima over here, some other minimum over there, over some free energy barrier, right? But if we start simulating an MD simulation that projects to this minimum, and we don't know anything about this minimum, we don't even know it exists, how do we find it? Well, we could make this guy explore feature space, and maybe we get lucky and we find it, or maybe not. If we know this space, this other minimum exists, now we can do a very precise calculation. We can say exactly how much free energy does it take to go from one to the other. We do that by finding the minimum free energy pathway. All right, the pathway that has the least cost in free energy to go from one minimum to another. So instead of doing one MD simulation that maps to one point in feature space, we do a series of MD simulations in parallel. Each one maps to its own point in feature space, okay? Those points in feature space are tethered to each other along a chain or a string, we call it a string. So image 1 is tethered to image 2 in the feature space, 2 to 3, 3 to 4, and so forth. So they're all connected. The MD simulations aren't connected to each other. They're running independently, but the points in feature space are connected. And then we can say, okay, this is now a one-dimensional object in feature space. We want one end to fall into one minimum. We want the other end to fall into the other minimum. And we want the string to go over the saddle point, right? That's what we want. So if you consider each point in the string as an independent system and you run tanh, and you say, okay, let's make the tanh temperature 0. That's steepest descent. You will fall to the closest local minimum. You will fall in there. So I have a string of systems and I say, okay, turn on steepest descent. This half will fall into that minimum, these half will fall into that minimum. I don't know anything about the saddle point. Okay, so that's where these connections come in. We force the systems to be connected to one another along the string. All right, so they repel each other along the string. So if I start with a string like this or like this, it doesn't matter how I do it. This then falls into a minimum, that then falls into a minimum, and the intermediate states are connected. They maintain the string. And because I'm using steepest descent to move these images, the ones that go over the saddle point will find the saddle point, right? The saddle point is minimum along all but one direction. So the one direction it's not a minimum on, I'm tethering to the other string, the other images, or the one direction in which the eigenvalue is imaginary, whatever, eigenvalue is negative, okay, fine. So, but it's finding that one saddle point as a result. So it's a very simple prescription. I've just described it to you in words. Here it is in a set of equations. So all we're doing is starting off. So this it's a little hard to see. This is a Mueller potential. So it's got a minimum here and another minimum there. If I start off with this set of images in the string and I want to find the pathway of minimal free energy to take me from that minimum to that minimum, I can start running string method. And if the thing is doing steepest descent to start with, the whole string is moving. And then eventually it will deform conform to the minimum free energy pathway as the two endpoints fall into their closest free energy minimum. Now, this is an optimization. Depends on the initial condition, obviously. So when one does string method, one likes to begin with a string that is roughly where you believe it should be, and then allow string method to find the converged minimum free energy path. This is a toy example because there's no MD simulations going on here. This is a well-known free energy surface. But you have to imagine that each one of those little dots has associated with it a full-blown MD simulation that's running and capturing these mean forces. And then on regular intervals, you can do it every single MD time step, or you can do it every 100 time steps or whatever. You tell these points which way to move. And they move according to which direction you tell them to move. Okay. So string method was well established when I started working with it. But one thing I thought was interesting was to, instead of forcing a string to connect to minima, excuse me, we could also tell the string, start from a minimum and find the closest saddle point, climb up to the closest saddle. Okay, so in simulation, or in the world of metals and hard matter, you may know the nudged elastic band method. This is inspired by that. Nudged elastic band works on potential energy surfaces. This works on free energy surfaces. So that's the main difference. Plus, it's also not an elastic. It's not elastic band with two images. We have as many images as we want. Okay. So the idea is now we have a string where we have an endpoint who undergoes steepest descent. So it will fall into a minimum. The other endpoint also does steepest descent, except we take the component of the instantaneous force that acts on the end that's tangent to the string, and we flip it. So it always wants to climb, okay? It'll always want to climb up. So this is the operation we're doing. This is the tangent vector, the local tangent. We simply invert it. We negate it. Now the image, the force that acts, or the evolution of that end point is climbing up the free energy walls. All the other points, no, they want to fall down. So this guy's climbing up and dragging his partners along with him. But what that guarantees is that you find a saddle point that is connected directly to the basin you start in. If you've done nudged elastic band, you know that doesn't necessarily always happen. With nudged elastic band, you can hop basins and get to a saddle point that's not connected to the minimum you start with. With climbing string, you're guaranteed to get to a saddle because it is literally connected. Okay. And we can tune how fast the climbing goes by tuning that so-called friction point. Okay, so I want to compare two versions of climbing string. Okay. So something where we've got, now these are actual MD simulations. These are, so when I say, what is the hydrogen atom of proteins? It's a metaphor. What is the hydrogen atom of proteins? It's alanine dipeptide. So anything you want to test out, any method you test to do for proteins, you start with alanine dipeptide. It's alanine dipeptide, okay? It's the psi angle, the phi angle. So measuring the conformation of alanine dipeptide. There is a very, very clear minimum for alanine dipeptide, or sorry, maximum, sorry, it's a maximum. There's the minimum, one of the minimum. And we say we want to find the closest saddle points. So we run multiple strings, multiple trials of climbing string that all start at this place. And each one of these are independent climbing strings. And we have to find a saddle point here. There's a saddle point there, there's a saddle point there. We want to find all those. We want the algorithm to find those. Okay. So when I do that, I need to start from the beginning. So there's where we started. Those are our initial guesses. Those are the initial pathways that we pick. And then we run them all. They're not running simultaneously, but we've put them all together in the same simulation. And you can see, yeah, we find all the saddles. But look, these two guys, the black guy and the yellow guy, find the same saddle. So that was a wasted effort, right? Why find the same saddle once? You've already found it. Okay. So was imagining in a more complicated system, you want to find all the saddle points that connect to a minimum. You really want to avoid finding the same saddle over and over again. You don't want to do that. So with working with a postdoc, not Alexis, but the next postdoc or two more postdocs after that, we developed an algorithm where essentially we run a couple of strings to start with. And every time one finds a saddle point, it marks the saddle. And then this acts as a repulsor. So it repels future strings. They don't go near it anymore. So in this climbing multi-strings implementation, I can now pause. In climbing multi-strings, it's much more efficient. So it already knows not to go there. So it shies away, and then it finally goes, oh, there's the minimum I want, or the saddle that I want. So because it already found this one, it doesn't climb very far close to it until it decides to flip around and try a new direction. And we still end up locating all the saddle points. Okay. Great. So there's the full map for alanine dipeptide that we found using climbing strings. So what you want to imagine, first of all, the beautiful rainbow colors there, which is really just a representation of the full free energy surface for alanine dipeptide. You imagine that it's not there. Imagine a white background. We don't know the free energy. Now we run these climbing multi-strings, and what we generate are these pathways where we identify every stationary point. There's a minimum 1, minimum 2, minimum 3, minimum 4. We find all the free energy minima, and we start in minimum 1 and we just climb until we find saddles. So we found S1, S2, S3, S4, right? Each one of those, then we could fall down into a local minimum. So in this climbing multi-strings approach, we're able to find all the minima and all the saddles. And that's a very simple system. Following this by that. Okay. So we wanted to do something a little bit more complicated. All right. What is one more complicated than alanine dipeptide is alanine tripeptide. Okay, so with alanine dipeptide, we have 4 minima. With alanine tripeptide, which now we have instead of phi and psi, we have phi 1, psi 1, phi 2, psi 2. So it's 4-dimensional. We have a much more complicated map. We can't represent the free energy in 2 dimensions, but now we've gone beyond the need to represent the full free energy. All we really care about are the stationary points. Where are the minima and what saddles connect those minima? So of course, it's much too complicated a network to make much sense out of, other than to ask some questions and see what the answers are. So one of the questions we asked, well, how do we get from minimum 7, which is in the middle, to minimum 14, which all of a sudden I lost. But we just focus on M3. We worry about that one. So M3 is up top there. All right. So we have 2 pathways we can follow. We can go from M7 to over the saddle at S30. So that's to here. So one shot, and that gets us from one minimum to the next. Or we can go over saddle 46 to M8 and over saddle 34 to M3. And these, when we align up the free energies, we see that, of course, the free energy penalty to go over through this intermediate minimum is much lower than to go over this saddle point S30. So the power of being able to build a network using climbing strings is to be able to ask these questions. What is the thermodynamically easiest pathway to go from one minimum to another? And if one knows that about a particular system, you could argue you know everything about that system. You know how it transitions from one state to the next. So if you really understood the structures that give you, that stabilize M8, right, and you wanted this pathway to be even more important, you can imagine making changes to the system that deepen that minimum, for instance, right? But without the design information you get from mapping the network, it's very difficult to answer or ask those kind of rational questions. Okay. All right. So I come now to Markovian milestoning. Okay. Let me go back one question. Okay. Which of these pathways is faster? Happens in the least amount of, happens in the shorter amount of time. Which one happens in the shorter amount of time? The red one or the black one? You would think the red one, right? It's a lower free energy barrier. Okay. You're probably right, but you don't know. You have to measure it, right? You don't know. When you go from one minimum to another in feature space, and you have multiple pathways, and which pathway is faster, the right way to phrase that question is, which pathway has the largest reactive flux, right? So you imagine You start off in this one minimum and you run an infinite number of MD simulations. How long do we wait for an infinite number? A long time. Okay. And you just keep track. How many of them wind up in the target state? So that's an ensemble of trajectories. Okay. Now you ask, what is the average time each trajectory took? And that's your mean first passage time. And then you can bend them into which pathways they took. A mean first passage time for pathway 1 and a mean first passage time for pathway 2. The expense to learn that information is running an infinite number of MD simulations, which we don't want to do. Okay, so we'd like to be able to say, okay, which one of these, this may be a faster pathway. This what we don't know is, this is a one-dimensional line. We don't know along the pathway how wide the pathway is, right? A wider pathway can have more reactive flux. Essentially, you're asking what's the entropy of the path, right? We don't know that. So this could be a very skinny pathway through a very precise amount, I have to use a basketball analogy. So Caitlin Clark plays for University of Iowa, is the leading basketball scorer of all time now. She can make a basket from half court easily. That's extreme. Can I? No, I cannot. I will miss every time, right? But she can create a reactive flux through the basketball hoop very precisely. But if I'm doing it, no, I would rather get very close to the basket. So the point is that pathway is very narrow. It takes a very, very special kind of trajectory to get to that pathway. And Caitlin Clark is rare. She's 1 in a billion. So of course, if you wanted to ask, take the average person at half court and ask how long will it take for one shot to go through the hoop? Could be an infinite number of shots, right? Could be a large number, but it's quantifiable. And again, in the metaphor of an MD simulation, it's also quantifiable. So Markovian milestoning is one way to try and do that, to try and understand which pathways are fastest by measuring reactive flux. So I'll use another analogy here. This is a topographical map of a very special place. It's called Medicine Bow, Wyoming. So Medicine Bow, Wyoming is, you guys think you have mosquitoes here. No, you should go to Medicine Bow. They are this big and they come in these huge clouds. And yeah, mosquitoes here, but they're also not deadly in Medicine Bow. But there's many, so say for instance, this is a nice little lake to camp around, and say you want to get to this lake or you want to go to this lake up here. You would really want to have information, not only where the trail is, but these trails go up and down and around. They have switchbacks. How long does it take? You're planning your multi-day backpack trip. You don't want to, we're going to go from this lake to that lake. And is it a 2-hour hike or is it a 12-hour? You really like to know. So, well, how do we know that it's a 2-hour or a 12-hour hike? Somebody went and did the hike and calculated, right? They didn't look at the topo map and estimate it. No, they did it, right? And probably it was many people who did it. At certain times of year, maybe more difficult. It may take someone like me a very long time. Someone like one of you guys may take a very short time to do it. So there's a lot of variability. But the point is that it's measured. Okay, so we think of a molecular system as having this topographical map of where the stationary points are, and we want to understand, well, how does it get from one point to another? Which pathway takes the least amount of time or has the most reactive flux is a similar kind of task to try and do it. Have multiple measurements to try and get at that information. So Markovian milestoning is a derivative of milestoning. Milestoning is a product of Ron Elber many years ago, and it's a simple reconceptualization of an MD trajectory by taking the space the MD trajectory lives in and dividing it into cells. In every cell, there's a boundary between cells. The boundaries are called milestones. So these lines here are milestones. The cells have these numbers. And so milestone S12 is the boundary between cells 1 and 2, S23, the boundary between cells 2 and 3. And this little wiggly line is the MD simulation moving through configuration space, okay? The idea is that once you have this conceptualization of configuration space, the trajectory turns into a jump process where the instant it passes a milestone, it changes state. So it goes from black to red. So it's in the red state. It spends some time in cell 2. We don't really care the details of what it's doing in cell 2, but then it jumps to the blue state by crossing that milestone. So now it's in the blue. And you can build this up. So every time it crosses a milestone, it changes state. So that's an MD trajectory. That is 3n degrees of freedom evolving discretely in time. It's an enormous amount of information. It becomes a very simple jump process where you have states with lags, right? So this is in the state S12. There's a lag at time T12 super 1. So these are lag times. These are the states that it's in. And now you can talk about the probabilistics of how long the lags are and how likely you are to transition in a given amount of time. So you build basically a rate matrix from the jump process. Now, turning an MD simulation into a jump process, again, you have to run the thing and then convert it to a jump process. And now you have a way to describe the dynamics, which doesn't require all the atoms. But you had to run the simulation to generate the jump process. So have you really gained anything? Well, it's a different way of representing it, but you may not have gained much. Okay. So with moving from milestoning to Markovian milestoning, now the idea is that we know something about the system. We know where the minimum free energy pathways are. We can focus the sampling along the minimum free energy pathways, all right, and build up free energies associated with being in cells along the pathway. So this is just details that are explaining how we, instead of with regular milestoning, we don't have the probability of being in any one cell. We don't need. Here we do. We track that explicitly with a master equation. So we can reweight all of our trajectories according to the probabilities that they're in each cell. So we can go back here. So if we were to imagine this trajectory, or that's a direction in this 4-dimensional space, I could divide 4-dimensional space up into these adjacent cells along each pathway, all right? And run simulations inside each cell and get statistics on how long it takes to go from one milestone to the next in each cell. And then essentially integrate that to get a mean first passage time to go from one minimum to another. So that's what we're going to do for this system. Okay, so this is monomeric sarcosine oxidase. It's an enzyme. And as the name says, I didn't write out monomeric sarcosine oxidase, but it's an enzyme that oxidizes sarcosine. Sarcosine is an amino acid. When you oxidize it, it becomes glycine. It's a flavoprotein, a flavoenzyme. There's a flavin group. This ring system here is flavin. It's a redox partner. So the job of the flavin is to be an electron transfer agent so that you can oxidize the substrate. So the reduction of the flavin is coupled to the oxidation of the sarcosine, and then something has to come back and regenerate the oxidized flavin. That's molecular oxygen, O2. All right, so this is an enzyme that requires, once it oxidizes substrates, it has to be reoxidized with molecular oxygen. Okay, so the flavin site, the catalytic site is buried deep in the middle of the protein. And this red blob is just a measure of the cavity inside the protein where the reaction can occur. This is based on an X-ray structure. Okay. To connect that cavity with the outside of the protein, there are several channels to get from the solvent to the inside. And we wanted to measure essentially how long it takes molecular oxygen to get through those channels. Now, we weren't able to simulate sarcosine or glycine doing the same thing because they're too big and complicated as of yet, but molecular oxygen was pretty easy. So this is a reaction network that has two competing mechanisms. We want to understand which mechanism is more likely. So I'll start here. This is the power stroke. We've oxidized flavin and we have reduced substrate. The objective is to go from reduced substrate to oxidized substrate, or oxidized substrate, which is in a product, P. This is oxidized product. So in that power stroke, the flavin is reduced. So to reoxidize the flavin, the product is released. You have reduced flavin, molecular O2 comes in, releases hydrogen peroxide, and now you have oxidized flavin. So the next substrate combine and you can repeat the cycle. So very simple. This mechanism is called ping pong because you have one thing happens on one side, and another thing happens on the other side. Like that, ping pong. I didn't come up with the name. That's what they call it. Okay. Now, the alternative is called modified ping pong. Very, very original name. In modified ping pong, the only difference is that oxygen comes in before the product is released. Okay. And I don't want to talk about why it's important to know which one is which, because I believe it's important because they're different. You just want to know. But as an engineer, I have to convince engineering audiences that there's a reason you should know this. Who's an engineer? Great. Okay, I don't have to explain it anymore, just because you want to know. Okay. There's a different mechanisms. It's just a matter of which happens first. Does the product get released first, or does oxygen come in first? Okay. Okay, so if this modified ping pong mechanism happens first, if the oxygen come in and then the oxidation happens and the product is released, and you now have your oxidized flavin ready to go through the cycle again. Now, I didn't come up with this question. People who study this enzyme, enzymologists, came up with this question. They answer this question by doing experiments and plotting the results on a Lineweaver-Burke plot. If you've taken biochemistry, anyone taken biochemistry? Not yet. Maybe you will. Lineweaver-Burke plots, you'll learn about Lineweaver-Burke. So this is a plot of 1 over the turnover rate. So it has dimensions of time, 1 over turnover rate. So how long does it take the enzyme to do 1 turnover? All right, versus the reciprocal concentration of the substrate, sarcosine. Okay. Each one of these lines is a different oxygen concentration in the water where the reaction is happening. And as you get to this point here, this line at 1.27 millimolar oxygen, that's essentially running with saturated oxygen in the atmosphere. As much oxygen as you can get into the water. Okay, now, if the ping pong mechanism is the right mechanism, that means that the turnover rate relation to the sarcosine concentration must be independent of the oxygen concentration. Okay, they're completely separate. If they're separate, it's a ping pong mechanism. When O2 is binding, the product has already been released. So there should be no dependence they should be independent. However, when you fit lines to these data and then you zoom out, the experimentalists find that the lines are not parallel. They have an intersection point. So this led the experimentalists to conclude that modified ping pong is more likely because depending upon the concentration of oxygen, you get different kinetics, different rate at which the product is released. So the hypothesis is that since modified ping pong implies the kinetics of O2 entry and exit are sensitive to whether or not substrate is bound, we can run simulations to test that hypothesis. We can run simulations with substrate bound and with not substrate bound and compare and just see does it make a difference. So that's what we did. So this is a representation of all the Markovian milestoning MD simulations that we did to connect the catalytic site here with all of the entry and exit pathways that an oxygen molecule can take to get from the solution into the active site. And I don't know if you can see the little balls. Those little balls represent milestones, or they represent the centers of cells between milestones. So these are minimum free energy pathways that we computed using string method. The string method to compute minimum free energy pathways. Once we have the pathways, we can do these milestoning calculations where we run individual MD simulations inside each cell. Right, and if the system tries to leave that cell, we just repel it back into the cell. We just gather those statistics on how often it tries to leave. We do that, hundreds of times for all of these cells, and we can build up an overall rate matrix for that system, and talk about which pathways are faster and slower, and whether or not if there's a sarcosine bound or not sarcosine bound, whether or not the kinetics of O2 entry and exit change. Okay, so these are the results. So in this table, I'm plotting the K1, that's the first order rate constant associated with oxygen getting into the system. And then experiment reports this quantity, KO2, which is the first order rate constant associated with oxygen being consumed. So these are different quantities. This is oxygen getting in. This is oxygen getting out, K minus 1. So we're measuring this reaction, the kinetics of this reaction. Reduced enzyme plus O2. O2 comes in, we have reduced enzyme complexed with oxygen. And of course, if oxygen leaves before this happens, then we have the reverse, so K1, K minus 1. These are the two things we can measure with milestoning. Okay. The experiment measures this entire process. That's KO2. So what we're missing, of course, is the stroke where chemistry happens. And we can't do chemistry with these force fields because they are, of course, non-reactive force fields. So this is not a process that we're simulating. We're covering this, and now we're asking, in the case where we have this Apo means that the enzyme does not have substrate bound, and hollow means the enzyme does have substrate bound. And we see different kinetics. So the first thing that we conclude is that with the kinetics of O2 of this reaction, the kinetics of that reaction depends upon whether substrate is bound. That changes somehow the pathways that oxygen uses to get in and out of the enzyme. Okay, and now we can address each of these pathways individually. So here's the case with no substrate. Here's the active site. And we have these three major portals to the solvent. We call them SARC, mid-lyse, and gate lyse. Sorry, we can make up names, so we made up names. And of course, the red arrows are oxygen coming in. So we have rates of 200 microseconds, 700 microseconds, 900 microseconds to get in, and then very fast rates getting out. So with the APO system, it takes a long time for oxygen to find its way in, and once it's in, it can get out very, very easily. Okay, and we're running everything under this sort of saturated oxygen concentration. When the substrate is bound, it closes down this mid-lyse pathway altogether, and it greatly changes these other pathways. Okay, so the kinetics associated with these other pathways goes down by an enormous amount. So when the substrate is bound, it's really trying not to have oxygen come in or out at all. It's really trying to shut down the entire enzyme. So we see that by those direct measurements. So that's all I wanted to talk about for monomeric sarcosine oxidase and Markovian milestoning. So I'll summarize here. So OTFP on-the-fly parameterization combines the enhanced sampling of TAM, temperature acceleration, and free energy profile generation. So we get a deeper understanding of certain biomolecular mechanisms. And I showcase some of Alexis's work where we recapitulated this knock-on transport of potassium ions and also show that dry transport has reduced barriers. So that's an outstanding prediction that we don't know if it's true or not. And then switch to the climbing multistrings method for locating stationary points in feature space. And then finally, as I just finished here, I demonstrate Markovian milestoning along a minimum free energy pathway to estimate entry and exit rates of O2 from MSOX. And I will argue that I think the simulations agree that modified ping pong is a more likely explanation for the kinetics than is regular ping pong, because the substrate does influence O2 entry and exit kinetics. So at this point, I would like to acknowledge everyone who did the work. So of course, as I already said, Alexis did the OTFP and TAM work that I illustrated before. My postdoc, Gaurav Srivastava, who's now back in India, did climbing strings. And Anthony Bucci was a PhD student who did the milestoning work. Funding was from NIH and NSF. And then I finally have some GitHub repositories here that you're welcome to clone and fork or whatever you kids do with these nowadays. So that's it. Thank you very much for your kind attention. Yes, thank you.
Yes. Well, do you have any questions?
Yes, I'm.
Very nice talk.
Thank you.
It was a pleasure to hear you. What do you think that is missing, if there's anything for these techniques to be adopted by mainstream? I mean, people that just do not develop method, but they apply it in
Such a good question.
everyday.
Yeah. Documentation, better software, and yeah, just a lot more examples of how they're used. So the question is, what will it take for some of these methods to be adopted more widely by people who don't develop methods? This is I could have a long philosophical discussion about whether that's even possible. Yeah, so I guess I'll say I'm ending my talk with my GitHub repositories, and each one of them is progressively more well documented, better documented. And I actually had a paper published on a separate code recently. So I myself am evolving into becoming more of a developer, not just a software developer, not a method developer. Software development is the key. I think you're going to have, if you can pip install it, then someone can run it, right? You can't pip install OTFP, I guess. Have you made it so it's pip install? No, probably not. Pestifer is a code that generates initial conditions, sort of like charm GUI, but it runs locally, so you don't have to do charm GUI. You don't have to, if you have a very secret protein structure, you don't want to give the charm GUI people that structure, you can use PESIFER locally instead. That's very well documented because I'm trying to publish it. OTFP, Alexis, you and I probably the only ones who know very well. Yeah. There are unfortunately many, many more people who develop these methods than people who develop software to make the methods useful. So yeah, I would like to see, governments, foundations put more effort into software development. So NAMD, heavily supported by National Institutes of Health. GROMACS was heavily supported by the European Science Foundation. Yeah, this is what you need. And they have teams of people who keep that software up to date. This is just me. I'm supported, but but yeah. And I don't think showing allene dipeptide again makes anyone want to use the method. Yeah, it's just, but maybe tripeptide. Fine. Good question. Thank you.
Another question? I have a question. The HIV spike protein that you show, the two conformations, you say that you can stick an antibiotic there, right?
An antibody, yeah. It was
Antibody.
yes. That is
Okay.
the whole nature of HIV research now is to figure out how to make the protein elicit neutralizing antibodies so it can be a vaccine. But
So this is kind of a weakness of the virus, if you can. This one or this one?
HIV is it's a strength of the virus. The spike protein in particular is very, very good at tricking the human immune system into generating an enormous number of antibodies that are not neutralizing.
So it may be a place to just attract antibodies.
Yeah, and that's an example. 3HI1, that's the F105. F105 is a very old antibody discovered in an HIV patient. And if you take F105 and purify it and give it to someone who's infected, it doesn't do anything. It doesn't neutralize the virus. But that's the crystal structure of that piece of the spike protein when it's bound to that antibody. And it's still a huge mystery. This is the current project I have ongoing with my other collaborators, is to try and figure out what is the right structure of the spike protein that generates neutralizing antibodies. Almost everything you do with spike protein to generate neutralizing antibodies gives you non-neutralizing antibodies. There have been 26 HIV vaccine trials. They all fail. They're using different versions of that protein. They all fail, but they generate a lot of antibodies. The people that are vaccinated generate tons of antibodies, and they're no good.
Wow.
Yeah. So it's a huge, huge problem.
Okay. And so another question. This is, COVID and
Yeah.
This spike protein is similar to COVID. You expect that COVID has some of these
No.
fake weakness to.
Nope. COVID is
No.
COVID's very simple. Yeah, that's why the vaccine worked the first time. The spike protein for COVID, they're both HIV spike and COVID spike. They're both class 1 fusion proteins. That means they have the same rough mechanism of operation. But the COVID spike is very stable. It only took a couple of little engineered mutations to generate the RNA sequence that codes the COVID spike, so that the human body could generate very stable versions of that protein that are immunogenic. They generate neutralizing antibodies. And the latest vaccine trial for HIV is the same technology, messenger RNA, coding for the viral spike protein for HIV. It's not the right conformation of HIV. It will not, it hasn't been proven yet. My prediction is that it will not work because it's not stable. It's not the right conformation. If it works, that's great. But they're very different. COVID spike is very stable. You know how many structures there are of COVID spike in the database now? Hundreds. They just proliferate. It's crazy. They're extremely stable. And it takes, and they're all different species. right? Every species of SARS-CoV-2 that has any number of people infected with it will have this spike protein because they're all very similar. HIV has what, 12, 14 clades have been evolving for the last 40 years. And they're basically, so there are hundreds of subspecies. All of the structures for HIV spike protein in the database come from 3 species. The vast majority from so-called DG505, which is irrelevant. But it's very easy to get a structure of, very stable. That's not an actual spike. So anyway, I could go on. It's like, yeah. And I would love to talk about the HIV work. It's just too new. So yeah.
But I have another question.
Okay.
You say that.
Yeah.
Sorry, the last one, Mike. So we should be afraid of COVID evolve to something like that to get more diversity in the spectrum.
Oh no. I need some Malbec before we discuss that.
So you can do.
Do you have money to give me to do research? Then I will tell you yes.
Yes, have to be afraid.
So I honestly, I am 1,000 times more afraid of HIV becoming airborne than I am of COVID getting any. COVID is just a respiratory virus. Like true, they can be very, very bad. Right? Respiratory can be very, very bad. The technology nowadays wouldn't allow the plague to happen, the Black Death. We have so much technology now that would never happen. But if HIV could be transmitted by saliva, and physically speaking, SARS-CoV-2 and HIV, they look the same from the outside. They're lipid membrane enveloped viruses. They're about 100 nanometers in diameter. They have, SARS has maybe 100 spike proteins on it, and HIV has maybe 10 spike proteins on it. Not that different. But the spike proteins for HIV they are very particular. They decay very easily. They're very unstable. And so if you put them in water, they can fall apart. This COVID spike's very stable in water. They're very happy. And so, but I think there probably are, who knows, 2 or 3 mutations that could happen for HIV to make it stable and still infectious. It's a very narrow window, right? If a virus, HIV emerges that is stable in water, we're in big trouble. And we're very lucky in a very bad way. HIV is evolving fastest in sub-Saharan Africa, where there's no COVID, right? There's no COVID there. But if one person is infected with both COVID and HIV, and it happens to be one cell that has both viral genomes in it, and they happen to mix, and maybe HIV, like HIV infects your immune cells and COVID infects your epithelial cells, but maybe a stable hybrid spike arises from that is stable in water and still affects your immune cells. Oof, yeah, this is what I worry about. Yeah, but I don't worry that much. I mean, it's when you get deep into the work, you forget that you're.
Maybe also with mosquitoes.
Yeah. Yes.
Well, I was just going to comment that the selective pressure is kind of different, right?
Yes. Oh, very different. Yeah.
So in COVID, you basically get very strong selective pressure to accumulate mutations.
Yes.
Besides that, the antibodies already have good access.
Yes. Exactly. Yeah. Exactly.
So that's
Yeah.
why we see such fast evolution.
Yeah.
But my question was about MSOX. You commented that you didn't do what's the limiting factor to be able to simulate the coming in and out of the substrate and the product?
Too many. Well, it's the dimensionality of feature space. So in this case, feature space is 3-dimensional because it's the XYZ position of the oxygen molecule center of mass in a protein fixed coordinate system. Sarcosine, yeah, it has a center of mass, but it also has orientation and internal. So I need 6 or 7 degrees of freedom. And it's a curse of dimensionality. That's why. And we have been trying. Actually, we have been trying for the last 3 years to do benzamidine and trypsin, which is again like hydrogen atom of protein ligand interactions is benzamidine and trypsin. And with 5 degrees of freedom, we get the right answer with benzamidine, but it takes 10 times as much compute as other methods. And so we don't want to publish it. We haven't figured out how to make it work efficiently. So to answer Marcos's question, how do you get people to use these methods? You prove that it works on a real system. We haven't done that yet. Honestly, we haven't done it yet.
Pago,
Yes. I see that many methods have a few things in common.
Yeah.
You study all, there's overlap in some point. Do you envision a possible unifying theory or unifying method that joins all these ideas that are growing up?
Yeah. Again, I think Malbec would probably help me come up with that. Yeah. Yeah, that's a great question. I don't think it's extended Lagrangian. I think this goes back to the curse of dimensionality. I mean, there is research in automatically deciding what are the right collective variables, the right feature space variables to use. I've only ever picked them using my own intuition or letting others pick them based on their own intuition. But often, as in the case of the benzamidine example I mentioned, we pick them and they're wrong, they're bad, they're too much degeneracy makes it impossible to sample. A piece that might unify this approach would be a way to at least quickly evaluate different choices of degree of collective variables, or at least look at the system and how it's behaving without collective variables and say, okay, what are the right collective variables if I want to go from here to here? Right now, we're using intuition. We know roughly what direction it has to go, but we don't know what twists and turns it has to take. That's for me, the biggest issue. And there are methods that purport to do this, and they end up with machine learning based collective variables, and that's great, but you can't ask why anymore, right? Why does it work? Machine learning works. Okay. Doesn't get, for me, I'm very uncomfortable with that. I don't have any insight. But that's what Eric Van den Dyne works on now. That's why I'm not working with him anymore. No, it's not really why. But I just don't understand it very well enough. But getting back to this idea of how do you pick the right collective variables to answer the question you want to answer, that'll make a big difference. Yeah. It's the hardest thing for a new person to understand coming into this. Why did you pick those variables? Can't really. Like, and how do they think they could come up with the same idea that you came up with? It's difficult. And if you let a machine do it, everyone gets the same answer. Great, but we don't know yet. So, thank you.
Bueno, ¿alguna otra pregunta? Bueno, entonces, agradecemos a Cameron de nuevo.
Facultad de Ciencias Químicas.